Um, Hello, everybody. So this is Umberto Martinez speaking from Copenhagen in Denmark. Let me first thank you for thank the organizers for inviting me at this series of lectures to give my contribution and talk about atomic scale simulations for photovoltaics applications. I'll try to give you some insights of from what we do in the semiconductor industries. So myself, I've been working in the field in atomic scale simulation for quite a few years. So a comment. You can hear me. For a few years now, and so doing research in the university, but I've been working in this commercial environment for about 4 years now. 4 years working at what was QuantumWise. QuantumWise was a Danish company where we develop the code that I will highlight during this talk. And we used to support our academic and commercial customers since basically last year, September 2017, the company has been acquired by Synopsys, and that's why I'm here now being part of this bigger organization. This is a brief outline of the talk, so I'll spend a few words saying who we are and what we do, and highlighting some applications of Quantum ATK, who's our atomic scale simulation codes. You can do many things with this type of simulation. So in the time that I have here, I will spend some words going into the details, talking about interfaces and how you can model interfaces, metal semiconductor interfaces. And then I have two specific cases related to photovoltaics and solar cells. And now how, for example, we can calculate photocurrent and including the effect of electron-phonon coupling. I will then pass the ball, let's say, to our friends of Colorado State University. They will say something about their research project who's currently they're working on. Let me start with the conclusion, but it's mainly my take-home message, which I hope I will be able to leave you at the end of this talk, and in particular that the atomic scale simulation can actually provide very valuable insights for the understanding of the material properties. And since this talk is very much focused on electron transport simulations and how they can help characterizing interfaces. This is very important because some features are really, of the interfaces are really a characteristic of what's going on at the atomic scale level. And the example that I will show is this specific example where interface states can be very detrimental for solar cell performance. And another key point that I would like to highlight is that you can characterize your system with atomic scale modeling, but you can now actually also use this output as an input for other type of device simulation models, and that's what we are doing now, for example, with TCAD simulations. So those are just here. I show just some key figures of Synopsys, showing our leadership in electronic design automation tools and being as an emergent leader in software quality and security. Not going into the details, but as I mentioned before, I just want to mention that we are now part of this bigger organization, which includes about 11,000 employees around the world. And Synopsys is really strong in dealing in the whole chain, going from silicon to software. And the Quantum ATK team, which I'm part of, we're part of the silicon engineering team in Synopsys, who's like pioneering
I'm still here, but I'm thinking about slipping out.
In doing TCAD simulations. for devices, especially from even down to 5 nanometers and below. And why do we need atomic scale simulations here? Well, we are interested in that because, as you all know, the time is by the time the scaling of devices continues, and it's not only the dimension that decreases for different type of nodes, but also the complexity increases. Specifically, before maybe we were only using silicon and then changing the architecture of our devices. Now it's really a more complex game where different type of materials are needed and different type of architectures. And for this type of, in order to understand fully this type of systems, we really need to go down to the atomic scale level. And this picture, I want to show what we talk about when we say atomic scale simulations. And here we report like different simulation methods. In the bottom part you see TCAD and macroscale simulation tools. As a function of the system size that you can simulate sort of number of atoms. And you can see that at the top you have like more high level, very accurate simulation methods like density functional theory or semi-empirical tools where you can really capture electronic components of your atoms. Those are of course very computational demanding methods which limits you by the number of atoms and the system size that you can study. So let's see, you can see that you can go from hundreds to thousands of atoms, and then you can use empirical parameters potential to go to millions of atoms. So in the tool that we developed, is what we call Quantum ATK software platform. We actually developed both DFT, semi-empirical, and force field methods. And everything is wrapped into a nice graphical user interface so that you can easily set up the simulations and analyze the results. The key feature that I will really highlight in this talk is the non-equilibrium green function method, which is what we call device simulation tool, which is coupled with all these different methods, which means that you can study electron transport, as I show in the next slide, but you can study, for example, phonon transport, not only electron transport, if you couple that very efficiently, for example, with force field, which means that you can start studying thermal transport properties and so on. So the key feature that really I will use a lot in the next slides is what we call again this non-equilibrium green function formalism in ATK, which you can couple with DFT or semi-empirical, and then you can study electron transport across interfaces. So here this is just a model of a metal semiconductor interface. You see this is silver, these atoms here, and these atoms here represent silicon. And we have a central region here which is coupled with the semi-infinite bulk systems. We can then inject electrons. This will be the picture, and then because we can apply a finite bias, so change the chemical potential of the left and right electron, we will have some electrons are transmitted and some are reflected. And basically, by calculating the transmission spectrum, we can then calculate the current. And that's within this formalism, especially if we use DFT, a key feature is that by studying this electron transmission through the interface, we can actually account for tunneling effects. So electron can go from left to right and propagate for tunneling or thermionic emissions and so on. So here are some examples, very briefly, of some of the materials that we can study. You can actually, depending on the, as I showed before, or the method that you use, you can study pretty much any material that you can think of. Thermoelectrics, 3-5 materials, 2D materials. This plot shows the band structure of a silicon nanowire. So you can also study very common material like silicon, but then not just focusing on the bulk properties, but having like a nano-sized system. You can study dynamic processes. For example, you can study like, can study like diffusion of atoms, diffusion of molecules at surfaces, calculate activation barriers, and this allows you to study aging, growth, and so on. In this example, we see the diffusion of arsenic and vacancies per diffusion in silicon. So we can really understand how atoms diffuse in your material. We can move to more complex complex devices as well, like for example these magnetic tunnel junctions. So, and that's in these cases, that's really when you need to apply spin polarization and spin orbit coupling, and then you can also go to study topological insulators. So, but those are just some examples. I'll go a little bit more into details on the methods and on some results for describing the simulations that we do for studying metal semiconductor interfaces, and which are indeed critical for devices, electronic devices, for many ways. Those are responsible for the charge injections into the semiconductor. So it's really important that we capture all the specific features of these interfaces. So let me start with these textbook pictures, which I believe you are all familiar with. So you see that this is a band diagram, we can call it. So we have a metal on this side. This is the Fermi level. It shows basically the states available, and you can see that we have a semiconductor on the right side. So, and that's a pretty common fingerprint of a metal n-doped semiconductor. So the key features in this picture are the Schottky barrier, which is indicated by this arrow here, which is the potential barrier at the interface, and by this depletion region, which is the semiconductor region where the electric field at the interface is not screened. So this is not a trivial, even to simulate such an interface, it's not trivial, because you need to be able to first to get the right description of the band gap and the level alignment. You need to be able to apply a bias, because you want to study electron transport, so you want to really apply a bias to inject the electron either from the semiconductor to the metal or the other way around, electrons and holes. And you need to be able to describe the intrinsic doping. So we can do all of these with our tools. And let me just show with the methods that I described before. These are results that are done with DFT. And those are the results for, you see in this upper picture, it's like the model used to calculate this density of state plot. We have a silver and a silicon n-doped. So you see that what we get out of this simulation is really like a metal semiconductor fingerprint. And if we study that in more detail, we can see that now we have a really atomistic results, meaning that we see this dashed line show the boundary between the metal and the semiconductor. However, we see that these metal-induced gap states propagate into a few atomic layers into the silicon side. And then another key feature is this depletion region, which is captured very well by these simulations. I do show this picture, which is very similar to the previous one, because it's for a lower doping density. Lower doping density means that your depletion region that we just mentioned, it's very long. So you see that in this case, it goes even about 20 nanometers. So you can immediately understand why you cannot really simulate this type of interface by just a few atomic layers, especially on the silicon side, which is the semiconductor side. So that's a critical point, that you really need these long devices, which we can treat fairly well with DFT. The next step will then be to apply a bias. So this is a typical result. This is an IV curve. So you see the current as a function of the applied bias. So from the applied bias on the source and drain. And the curves are for two different doping doping densities. From this picture, we can then do a lot of analysis, and the analysis that I show here is that how we can calculate all the details are reported in this reference is how we can calculate the Schottky barrier as a function of the bias and as a function of the doping densities. So this Schottky barrier, basically, we find that it's not just a simple energy difference between the conduction band of the semiconductor and the Fermi level of the metal. So by using exactly these methods here, now I just mentioned this application, this paper that has been published, because they really show, for example, this work where they studied titanium-germanium interfaces, the study done by GlobalFoundries and IBM Research. They really wanted to understand by changing the phase of the titanium-germanium polymorph and the crystallographic orientation of the germanium phase, in this case, what's the best combination that gives you the lowest Schottky barrier height. And they finally found that this would be the right combination. So you can see that by using this atomic scale simulation, you can really play around quoted, with different system, and then you can also compare, for example, in this case, a V characteristic, the simulated one and the measured one. This is another nice examples from IMEC that shows the interface between silicon crystal and amorphous titanium silicon compound. And I want to highlight this specific interface because it shows that you're not limited to study crystalline structures. So you can also have an amorphous compound, an amorphous system, or an alloy also on one of the two materials, which is very relevant for your applications. And here they basically done more or less the same analysis shown before. They do this projectile density of states analysis that shows a nice band bending and these metal-induced gap states. And then by basically studying many different interface structures, we can calculate which one is the most stable one with the tools that we have, and then compare to experiments. And here they saw some nice comparison. So let me now go to two specific examples that I wanted to mention about solar cell devices, and in particular this specific device. And the goal here is to understand why these type of solar cells are not as efficient as we can calculate from theoretical and other type of simulations. And we think there's something going on at the interface, and specifically we focus on this interface here. So now I already showed the results, this plot that you now should understand very well. So this is like energy, and again, in this dimension, we go all the way across our device. So you see that you have 10 nanometers and 10 nanometers for the two materials. This is a semiconductor interface, so you're not limited to metal semiconductor interfaces. But so let's analyze a little bit more in detail this specific plot. We can see that we have a calculate a conduction band offset of about 0.2 eV, which is fairly good. You can actually expect, you would expect a pretty good performance by just checking these parameters. However, we also find that there is some band narrowing close to the interface, and this is due by these localized gap states which extend into the gap region. We can of course look into more details into these states, and here we do, if we do a charge analysis in particular, and we zoom in the interface, you can see basically that these states in the real space, they belong basically to the copper atom and the sulfur atom. So this is a fingerprint of this specific interface. And in fact, if we compare with a selenium terminated interface, So we take another material, we immediately see that these interface states, they don't show. So a lot of work has been spent to really understand the nature of these states and to understand that it's not like just a computational artifact. And now that we are sure about this description and we have this input, now we use this input for drift diffusion analysis. So now we can basically give as an input not just the shape of the band edges that you would expect from non-atomistic analysis, but we can introduce this band gap narrowing, and we can give as a parameter the height of this step, the width of this step, and basically if you compare here we report the electron or hole density as a function of the position across your device. You can see the red line. If you don't include these gap states, basically this is the density of your holes. However, if you do increase in the simulation this step, the hole density immediately increased by 2 orders of magnitude. And if we go even further, we study the temperature-dependent open circuit voltage measurement from this type of simulations with and without these interface states. We can calculate this combination energy deficit, which basically we couldn't explain why is it so high without knowing and without introducing these interface states here. Another example that I like to show is like how we do photocurrent calculation from first principle and by including electron-phonon coupling. So here I take the example of silicon again, because we all know this is an indirect band gap. So we cannot just, in order to have a transition from the bottom of from the top of the valence band to the bottom of the conduction band, the photon needs to absorb a phonon as well, and this is not a trivial problem. And the theory is there, but mainly because this type of simulations, if you really want to do them from first principle, let's say with DFT, they are very demanding because you really need to calculate a lot of displacements and use big supercells, and that's not possible on a daily basis. So we apply here what we call the special thermal displacement approach to include this electron-phonon coupling, and we do that for a device, a p-n junction device. We use that as a case study of about this size, and again you can clearly see the p-n junction. This is a typical p-n junction where you have like p doped here. This is again the Fermi level, and n doped on this side, and we use this to study the photon energies and the current density as a function of the photon energy. So here we include, you can see these two lines where we show like the current density. If we don't include electron-phonon coupling, you have the blue line. Well, as soon as we switch on this interaction, and in this case at 300 Kelvin, you can see that at the energy, which is close to the energy of our indirect gap, you already have an increase of a couple of orders of magnitude of your current density. We can now use introduce also calculate the photocurrent, and we use that by using first order perturbation theories, and I refer you to these references for the full details of the theory. And we can study here, for example, the current with the IV curves at different temperatures, and by introducing or not electron-phonon coupling, and calculate basically by this intercept here at 0. We extrapolate the open circuit voltage, and then we compare with experimental data, and we show that you do need to include, a finite temperature effects in order to catch the good results, the experimental results. This is another way to see it. So we fix the temperature and we calculate again the open circuit voltage for different illuminations. And again, we see that if we actually don't introduce electron-phonon coupling, even at very high intensity, you don't even get closer to the open circuit voltage for lower intensity. So with this, I'd like to conclude. I hope I gave you some insight about atomic scale simulation. Again, I really focus this talk on the electron transport simulation and that we can use to characterize interfaces. I hope the last two examples really show that you need the atomic scale description if you really want to catch specific fingerprints of these interfaces. So which can be detrimental or can even be increase the performance of your solar cells. Because now that you know really the atomic processes, the atomic scale processes that occurs, you can think about how to increase performance. For example, in the case that I showed before, you can try to, for example, passivate these dangling bonds that you have at the interface. Another key point that we really apply on a daily basis for device simulations in the semiconductor industries, but that can be done in the last example I showed, is that you can use this as an input for other type of device models, where you basically you cannot use the bulk material properties. With this, I would like to stop. Thank you for listening, and again, I'll pass the screen to Colorado State University.
Okay, thank you, Umberto. Hopefully everyone can hear me. Okay. Hello, my name is Anthony Nicholson.
And I'm Anand Tyagarajan.
And today we'll be presenting our research work on density functional theory modeling of cadmium telluride photovoltaics. This work involves research performed during our internship training at Synopsys Denmark, where we use the Quantum ATK software that Umberto described in his presentation. I will go ahead and start by presenting some quick background on thin-film CadTel photovoltaics. Over recent years, CadTel has become cost-effective for electricity generation due to a low production cost, exceptional reliability compared to other solar cell materials, and steadily increasing efficiency. CadTel is also suitable for large-scale production, as shown on the image on the left. The image shows a CadTel PV solar field installed in Arizona that has the capability of producing up to 290 megawatts of power. The part on the right simply shows how CadTel PV is cost-effective compared to traditional energy sources. From some of these highlighted points, it's evident that CadTel thin-film PV is competitive for electricity generation. Here at CSU, Colorado State University, we focus on CadTel-based thin-film solar cells, and we're steadily advancing toward more complex configurations to achieving higher performing devices. The Next Generation PV Center has recently achieved highest record cell efficiency of 19.16%. And as polycrystalline CadTel reaches higher efficiencies, quantum mechanical modeling is necessary for further device improvement. That's why we're using DFT to explore two interfaces of our current device configuration as shown on the right. We're looking at both the MZO CadTel interface as well as the CadTel Tellurium interface. And I'll be briefly speaking about the current progress made on the CadTel Tellurium interface using DFT. The JV curve shown here shows the effect of tellurium on the device performance. This data was taken by Dr. Amit Munshi at our NGPV Center. And as you can see in the red curve, the solar cell device without shows a kink present in the JV curve, mainly due to inefficient hole carrier collection at the back of the CadTel device. Adding a tellurium back contact to the device establishes JV characteristics that allow for efficient carrier collection and significantly improves the device performance. However, we're left with a question that is difficult to answer with experimentation alone. And that question is, what are the main mechanisms in tellurium that cause such a benefit to occur? That is why we are using DFT to investigate why tellurium is so beneficial to the CadTel device. The first DFT model simulates the CadTel 111 tellurium interface. We use, as Umberto described in his presentation, a two-probe model that consists of a CadTel left electrode and a tellurium right electrode, as well as a central region that makes up the entire CadTel tellurium interface. This model has a total of 430 atoms, and it must be sufficiently long enough in order for us to capture the screening region within the central region to ensure modeling convergence. And again, we're using DFT and this model to determine the mechanisms at the CadTel tellurium interface that enhance device performance. The second model focuses on CadTel 100 tellurium interface. We use a different CadTel plane compared to the previous model in order for us to determine how the grain orientation of CadTel affects the overall electronic properties of the device. The DFT results shown here are for the band alignment of CadTel 111 tellurium interface. This plot is the projected density of states representation of the CadTel tellurium band diagram using first principles calculations to create it. We have employed the GGA plus Hubbard U correction to obtain the experimental band gap for both CadTel as well as the band gap for tellurium. The conduction band minimum and valence band maximum are labeled in yellow and blue respectively. We right away notice that there are electronic states that exist within the tellurium band gap. We also see a pickup in the valence band due to higher hole concentration in the CadTel layer. And the model also suggests some type of upward band bending in the conduction band. All of these effects in the DFT model are beneficial to the CadTel device properties and may explain why, experimentally, we see such an improvement in the tellurium back contact. This is the band alignment of the CadTel 100 tellurium interface, and it's very much different compared to the CadTel 111 tellurium interface. There are not as many prominent states that exist in the tellurium band gap as in the previous model, and also the conduction band doesn't bend upward as presented in the previous model. The lack of an upward bend may lead to recombinations at the back of the device. However, experimental data shows us that cadmium telluride preferentially orients along the 111 plane. So this model would just be a small fraction of what's seen in polycrystalline CadTel. To further support the DFT modeling results, we can look at the effect of tellurium on the depletion width of the CadTel device. Looking at the plot, we can see that the line labeled in black has no tellurium deposited and will lead to a greater depletion width. When we add a tellurium back contact to the CadTel, as shown in these other lines, we see that there's a decrease in the depletion width, which in turn will lead to the device working more efficiently. More work is in progress in the DFT models, but so far we can see how current DFT results show a valence band pickup at the back of the CAD-TEL layer and how it supports a smaller depletion width as shown in these experimental results. Therefore, a decrease in depletion width is mainly due to how tellurium causes an increase in the hole concentration at the back of the CAD-TEL as suggested by the DFT results. With that being said, I will go ahead and allow Anand to describe his progress on the MZO CAD-TEL interface modeling.
Anthony, again, I hope everybody can hear me. And the subject of my research is the device structure shown on the left, which is magnesium zinc oxide cadmium telluride interface in these specific orientations. This data is obtained from calculation parameters can be seen on the right of the screen. Used an SG15 pseudopotential within the generalized gradient exchange generalized gradient approximation functional, bulk, and interface. Whereas for the device calculations, we used a semi-empirical method, band gaps. Traditional DFT methods have usually resulted in underestimation of the band gaps, and that's the reason. Density mesh cutoff was 3,700 volt with a K-point grid of 2 by 2 by 1. Total model consists of about 600 atoms. And the motivation for this research using MZO as a window layer is shown below. Anthony spoke earlier about the effect of tellurium, which eliminates the kink and results in high-performing devices. This plot shows the effect of MZO before the incorporation of tellurium at the back. The brown curve shows a cadmium sulfide, cadmium telluride device, which has historically been used by several research groups in cadmium telluride photovoltaics. The green curve shows the IV characteristics of a cadmium telluride device using MZO as a window layer. MZO, with its higher band gap, gives rise to a higher voltage, a VOC, and its higher transmission of the solar spectrum leads to a larger current. And this is why it was determined that an alloying combination and 77% to achieve device performance. Initial modeling efforts have focused on simulating a zinc oxide and cadmium telluride model because of the inherent complexity of the ternary alloy that is magnesium zinc oxide, and also because of the fact that zinc oxide up to magnesium have the same word-side crystal structure. Shown below is a density of states representation of the band gap with respect to atomic position. So the x-axis here represents distance perpendicular to the interface. The axis represents what reflects the illustration below, and it was determined at every point along the length of the device, similar to plots shown by Umberto earlier. This is also a two-probe model using DFT with non-equilibrium greens. Since it was hard to find a suitable interface potential between the two materials, are zinc oxide and cadmium telluride. So on the left, we have the left electrode, we have zinc oxide, and on the right, we have telluride, and the central region basically is hard to find a suitable interface potential between these materials, and so they were relaxed using theory. It was also challenging to find an appropriate Hubbard-U parameter to match band gaps, but reasonable values of band gaps and band offsets were obtained using the GGA half technique. The interface appears to be pretty clean and free of electron states, although there seem to be some states. This plot also bolsters the theory. Zinc oxide does not create a significant band offset, right? Although there is some band bending in the valence band, which is not be beneficial. It has been proposed that magnesium zinc oxide creates spike, resulting in performance, and that is, and so are different variations of the same materials. In conclusion, density functional theory-based calculations in combination with non-equilibrium Green's function technique have been used for band alignment at the interfaces. The results from the cadmium telluride tellurium model support experimental results. Additional modeling and experiments are underway. Preliminary results from the zinc oxide cadmium telluride models seem to match literature data on conduction offsets, while the magnesium zinc oxide and cadmium telluride interface is the next step. I'd like to thank Dr. Humberto Martinez for being such a valuable mentor. Synopsys Quantum ATK for hosting us during the internship, Denmark Technical University for enabling access to computational resources, for providing us the opportunity to pursue an internship in Denmark. Finally, to all NGPB members for your thank you.
Thanks, you guys. I think we had some issues with the audio with the CSU presenters, so if anyone had any questions because they were maybe unable to hear them well, please feel free to type them into the chat window, or you can also use your microphone if you'd like as well. And if you had any questions for Humberto, please also feel free to type those in now as well. I see that there was one question regarding getting a copy of the slides. Are there any issues with that, Humberto?
No, we can definitely share the slides. Absolutely.
Okay, so if you'll just send me over a copy of the file, then I will post post something online when we share the video, and so there'll be a link to the video and to the.
Cool. Yes, there's a question. Yeah, okay, I see the question. Well, how does it scale? It scales well. It really depends on also on the hardware that you have. It scales very well with the parallelization. So because the parallelization is both over gate points and over energy points. So it depends what we are talking about with system size. But there are some methods that I believe I can dig in some some scaling plots. Maybe I can let you know exactly. Let me add that this system size is also general because it scales different if you increase the if you have seen the devices, if you increase the thickness of your central region, meaning in the C direction, and also it depends if you increase if you make your AB region larger. So that's also different. We have some benchmark data that I'll be able to send you. If you also have some input, like, because as I said, it depends if you have, like, example, nanowires or I believe we have your contact. If you have nanowires, then scaling of, let's say, you increase the thickness of the nanowires is different than if you have a fully periodic system. So that's why it would be nice to have also some input from the system type that you guys are investigating. I know it's an unknown answer, but I hope we'll be able to sort it out. Okay, we also look at the transport in zeta direction. I believe that, yes, that's what we did in all these examples that we show. So zeta direction, maybe we should define, with zeta direction we mean the direction, let's say, in the interfaces that we've seen. Zeta direction would be the direction perpendicular to the interface. Okay, so in the direction, let's say, again, in the examples before, parallel to the interface. You can do that, out of plane. You can do that, meaning that you will construct your device in the other way around. So yes. Go ahead. Anamorphic material. Is it possible? It's possible, yes. It's difficult. That's very relative, but it's possible. Also depends on the type of simulations that you want to do. I briefly mentioned an example where one of your electrodes, part of your material is amorphous, and that was for electron transport simulation. We have the tools. I mean, amorphous materials in general with DFT simulations are difficult, mainly because of, in general, you need a bigger system. So if it's crystalline, you only need, let's say, 2 atoms, and then it's fully periodic. If it's amorphous, you need a much bigger unit cell to simulate an amorphous material. So in this sense, we can say it's more difficult, meaning that you will need a bigger system. But it's possible. We have tools to build amorphous materials from a crystal materials. They're usually more efficient if you can have empirical potentials, because then it will be much faster, at least to make your amorphous material. But then you can, yeah, okay.
Looks like there's one more question or comment coming in.
Not sure I understand the questions. Like the interface problems that we show, both me and Anthony and Anand, those are electron transport simulations. So by using the non-equilibrium green function formalism, which is coupled with DFT. So the DFT part is, let's say, standard DFT methods. DFT has many problems, and one of these is that standard DFT underestimate band gaps. So we have some methods to correct for. Yeah, I'm still here. You're welcome, William. Correct. So all the methods are DFT and corrections to DFT, and non-equilibrium green functions are implemented in our code and in many other codes. Well, not exactly. Yeah, okay. You're welcome.
Okay. Well, are there any other questions, or before we let everyone go? It's late there in Denmark.
It's okay, a little bit late. But if anyone has any other question later on, they can write me an email. That's a good question. That's Humberto.Martinez@Synopsys. That's simple.
Okay. Well, thank you again, Umberto and Anthony and Anand. We appreciate everyone's time, and thanks to everyone who joined in and participated. I'll get a video of this posted, and also we'll get the slides and share it as well. So thank you again.
Thank you again,
please,
and thanks for giving me the time.
Absolutely, and if you'd ever like to come back and provide us with an update, please feel free. We'll look forward to hearing from you again someday.
Will do. Thanks.
Okay, thank you, everyone.
Thank you.